So in the last video, I introduced the tabular method for solving a specific type of integral where you had a algebraic function or power function raised to some power greater than 1. So in this case, we have like x raised to some power greater than 1. In this case, it's 5. Last time I only did x squared, I believe. So I wanted to do something a little bit more complicated to really show the power of the tabular method. Also, it only works if you have that type of a power function be multiplied by a trig or exponential function, because those tend to be easily integrable and they don't change much as you integrate. And so, again, the reason this table method works is because every time you differentiate your power function, it decreases by power by degree until eventually you hit 0. And so in this case, you definitely want to make this x to the 5th your u, and this cosine of 2x dx your dv. So I'm going to come over here. I'm going to have to write a little small just to make sure we have enough room. But we'll have x to the 5th here. And I'm not going to write cosine of 2x dx because it doesn't really matter, the dx there. We're just thinking about what the integral would be here if we integrated cosine of 2x and everything beyond that. So let's actually go ahead and try this out. So for the column here, and notice I put an actual table this time. For the u column, we want to differentiate and keep differentiating until we hit 0. So, and that's going to help us get all of our terms for our answer. So the integral of, the derivative of x to the 5th is 5x to the 4th. The derivative of 5x to the 4th is 20x cubed. The derivative of that is 60x squared. The derivative of that is 120x. The derivative of that is 120, and then the derivative of that is 0. So we're done in regards to our u. Next, we need to do a bunch of integrals. So the integral of cosine of 2x is sine, positive sine of 2x over 2. We have to divide by 2 because we have to think about the chain rule for when we're going in the other direction and we're multiplying by the coefficient on x. We have to think about, the reverse situation. When we integrate sine of 2x, well, the integral of negative sine of 2x is positive cosine, but if you have positive sine, that must mean you had a negative cosine of 2x when you differentiated. And then you would again divide by 2, but we already have a 2 there, so it ends up being 2 times 2 gives you 4. The integral of that, well, the negative stays because the integral of positive cosine of 2x would be sine of positive sine, but we have the negative out front. So sine of 2x, negative sine of 2x, and then it would be over 2, but we already had a 4 there, so then we have to multiply and we get 8 there. It's a little too big, so I'm going to make it a tad smaller. Okay, the integral of this is, let's see, the integral of negative sine of 2x is positive cosine of 2x, and that's divided by 16. The integral of this guy is positive sine of 2x, and that is divided by 32. The integral of positive sine of 2x is negative cosine 2x divided by 64. Now, you might ask, how many times you need to integrate? Well, you need to integrate as many times as you differentiate it. You need the same number of terms. Now it's time to see what associates with what. So we take all the u's and we associate them with the corresponding v's in this fashion. You go down one diagonally and you see what associates with what here. And so the next thing you want to do is you need to account for this alternation and signs. And this isn't anything, just like arbitrary rule. The reason you have these alternating signs is because this sort of a problem, if you did straight up, integration by parts, you're going to be doing iterated applications of integration by parts, and you have this minus sign out front. And if you do another integration by parts within this integral, you're going to have a minus times another minus, and that gives you a plus. And you just keep getting these this alternation between signs, and so we have to account for that. So of course the first term, right? So think of all this as like x to the fifth and the sine of 2x over 2. This is your first uv here. It's positive. Think about if you did another integration by parts wrapped in here, you're going to have another uv, and it's going to be positive, but it's going to be multiplied by this negative, so it's negative, right? And then the next one would be multiplied by another negative, and it would give you a positive, and negative, and then positive, and then negative. And then we are ready to write out our answer. And we just need to remember what it is we're solving here. So it's the integral of x to the fifth times cosine of 2x dx. And this thing is equal to, and I wrote that a little funky, equal to, okay, so we just list out these terms as we have linked them together. You sort of write them, the line shows that those two terms are associated, and this sign tells you what the sign in front is. So we have positive x to the fifth, right, multiplied by sine of 2x over 2. Okay, the next thing we are supposed to subtract 5x to the fourth times negative cosine. So now we have to account for that negative, and that becomes a positive out front. So it'd be cosine of 2x, and this is all over 4. Okay, what's our next sign? It's positive, but it's going to be positive 20x cubed times negative sine of 2x over 8, so that ends up being negative. So this is going to be 20x cubed times sine of 2x over 8. And then we have, I'm just going to move it down just a tad now. We have, let's see, minus 60x squared times cosine of 2 of x. So minus 60x squared times the cosine of 2x. All of that over 16. And then we have positive 120x times sine of 2x all over 32. Finally, we have minus 120 times negative cosine, so that ends up being positive. So cosine of 2x over 64. And remember, this is a indefinite integral, so we have a plus c out front. And this is not, the final answer, because you need to reduce all of your fractions here. But I'm not going to go into all that, because this isn't a video about how to reduce fractions. At this point in your math career, you should be pretty well proficient in doing so. I don't need to demonstrate how to do that. I just want to keep these videos as short as possible. So that would just be the last step, going through and reducing all your fractions. But the point of this video was to show you how powerful the tabular method is when it can be applied. And in this case, if you had something like x to the fifth in your integral, and you needed integration by parts, it would take forever if you were actually using it just straight out, writing each integral and each iteration of the integration by parts formula. At this point, if we had done so, we'd probably be on the second or third iteration only, and we'd still have a lot more work to do. So we see, using the tabular method, we got to the answer fairly quickly. And this is a beast of a problem. Hopefully you wouldn't see anything that nasty on a test, but you never know, you could. You very well could see it on homework. So this is a pretty helpful method. Okay, I'm going to make some more videos relating to integration by parts. I think the next one is going to be involving something called the wraparound method, and then I'm going to get into the reduction formulas, and that'll be it for integration by parts.